So today it is Monday, the 11th of May, and we start recording a thermodynamic lecture. And today I think, first of all, we will go over your questions. And secondly, I will give you some further lectures in order to progress. The progress is not a progress, it is a run through thermodynamics. But it depends on you how much you are learning, and at least when you go home to have a brief idea about the main aspects. I would like to ask you if you had a look to the recording of the former lecture.
Yes, look again to the BV and TS diagrams and some of the before, but I didn't rewatch
Yeah,
uh,
because
the generator and
yes, I think it is a help for you that you are finding this lectures registered, because the registration is in YouTube, and so you can use it whenever
mhm.
you want.
Yes, yes.
Okay, so take your time. And I also gave you open sources, a lot of open sources.
Yes.
Yes, you saw it. Yes. Okay. So I have to make screen. Okay, share. So you see my screen now?
Uh, yes, I do.
Okay. So we will learn first of all about combustion and how the calculation of combustion is occurring. Because nowadays, presently, most of the energy comes from the combustion, either in power plants or in internal engines and so on. What will happen in the future with this tendency to replace the fuel energy with renewable energy or bioenergy? It is another part. But you have to know from the beginning that if you use combustion of biomass, that is also a renewable source, pollutants and including CO2 are also exhausting. But this CO2 is a neutral CO2. I will explain you this idea. Neutral CO2. What is this? Because normally combustion means carbon plus oxygen equal to CO2 if the combustion is correct, is perfect. We are saying it is perfect. But whatever you are burning, for example, if you are burning wood, yes, it
Mhm.
is containing also carbon, and this carbon through combustion goes to CO2. This CO2 has the same effect as the CO2 from coal, for example, or from natural gas uh, or from oil. The difference is that wood is originated in a plant, in a tree. And this tree has run photosynthesis during its lifetime. Photosynthesis means what? CO2 is turned in presence of sunlight and the green chlorophyll to oxygen. And that's why we are saying that a forest is the lung of the world, because every green plant is doing during day or when it has light this photosynthesis and turns the CO2 into oxygen.
Mm-hmm.
We presume that a plant or a tree, up to the moment when it is used as fuel, is neutralizing a quantity of CO2 and turn it into oxygen. When it goes into combustion, it produces CO2, but this produced amount of CO2 is less or at limit equal to the amount of CO2 neutralized through photosynthesis. And that's why the bioenergy is considered not to affect the global CO2 level that is very, very high and developed in a very active velocity after the industrialization started compared to these days. And the CO2 level in the atmosphere is one of the cause for the climate change that from which a lot of other results are resulting. The sea level is augmenting, at the polar, the ice is melting, surfaces near the sea and the ocean will disappear. The temperatures are higher and higher. You see a lot of effects of the climate change in the temperature raising, lack of rain, instability, meteorological instability, temperatures, a lot of things, yes, from this CO2. So I think you understood this idea of CO2 neutral. So we are going back to our calculation of combustion. So you don't have to think when you see the word combustion that you are doing combustion of coal or oil or gas. The combustion can occur with all materials containing chemical elements that are easy to go into an exothermal reaction with oxygen. And these elements are carbon, are hydrogen, are sulfur, also nitrogen, hydrocarbons, and so on. So if you think about a solid or a liquid fuel, the chemical analysis of these in reference to 1 kilogram is the following. It contains C carbon, C kilogram carbon. It means C gram of carbons because the total is 1 kilogram. Small h of hydrogen, small s of sulfur, and so on. Oxygen, nitrogen. W is water. Humidity is always or in a larger or smaller range contained in the fuel. And A means ash. Ash can be present in a larger or smaller amount or can not be present as for gaseous fuels. But this kilogram doesn't mean a kilogram of coal. It can mean a kilogram of waste, a kilogram of cotton, a kilogram of grains, a kilogram of forest wood or forest residues, and so on. The gaseous fuel has also chemical elements included, but we are giving them not as real chemical elements, but as stable elements. That's why 1 normal meter, 1 M3N, yes, contains hydrocarbons, CO, CO2, hydrogen, nitrogen, humidity, and oxygen. And this F means fuel, F from fuel. So we are using the symbol, let's say, of CO, but this CO in brackets and F is a number, not a gas. It is a number. This unit M 3N square, yes, is a unit for mass. What does it mean for a gas? 1 meter 3N. It is a unit of mass indicating the quantity of a gas that under normal conditions is contained in a volume of 1 cubic meter. Normal conditions are represented by 0 degrees Celsius, meaning 273 Kelvin, and 1 physical atmosphere, 1 ATM, not bar and not AT, technical atmosphere. So I gave you now two very important information. This unit 1 M3N, N from normal, that is a unit for mass, not for volume. And also I indicated you the normal conditions for temperature and pressure, meaning 0 degrees Celsius and 1 physical atmosphere. Is it clear for you?
Yes.
We are speaking about a perfect and complete combustion. Complete means everything that can be used as in the combustion is used. You don't have any losses. Perfect combustion means that in the flue gases, you don't find any more elements that could be used in combustion, such as CO, for example. So if the combustion is not perfect, for sure, in the flue gases, you will find CO, in the case of solid and liquid fuel, or you will find hydrocarbons, for example, in the case of gaseous fuels. When we say gaseous fuels, don't think only to the natural gas. Natural gas that is in a high range methane, CH4. So you can think also about, for example, of biogas. Yes, you heard about biogas. Each fuel can have all these elements, stable or not stable elements, or it can consist only of one representative of them. Combustion means what? Chemical exothermical reaction. For example, carbon with oxygen, CO2, water with half of molecule of molecular oxygen, H2O, and so on. Important will be the last reaction, that is a general reaction depending on X and Y, because if you put instead of X, for example, 1, and instead of H, 4, you have methane, and by replacing in this general reaction the X and Y with the named number, you will find the exothermic reaction of methane. Yes?
Mhm.
As you see, CO2 is a reaction, is a result from all kinds of reactions, from the normal exothermal reaction of carbon, or the result of the combustion of the CO, if it was first not a perfect combustion, CO is resulting, and our interest is to use the CO in the further combustion process. But it can appear also from the combustion of hydrocarbons. As a result of the combustion, we have the CO2 already mentioned, H2O, water vapors. Water vapors and all gases that are containing 3 atoms in the molecule are considered gases that are contributing to the global warming, the so-called house gas effect. It's clear up to now?
I hope. I will search more for it
Yes.
to make
So
sure.
now we will write for each category of mentioned reaction a little bit in detail the combustion process, because I want to explain you the result of this combustion calculation, and demonstrate you that the formulas, even they are quite difficult to apply, they are formulas deducted on based on science, and they are not deducted from other considerations. So when we are running a calculation of the combustion process, it is important to know how much fuel I need in order to produce so much heat energy. This is the first step. Secondly, how much air I need, so how much oxygen I need to run such a combustion, to run the combustion of the fuel needed in order to have as a result the needed heat energy. But oxygen is not available in a molecular form alone, it is available, very available in the air, but it comes with nitrogen. The composition of air is well known. Do you know it?
Yes, it's 97% nitrogen and
So 21 and
3 I
79,
179.
yes,
Yes,
but
and
you,
others.
yes, and others, yes, but okay. But when you say 21 and 79, you must say that these are volumetric percentages, because if you are analyzing air from the as a mass, the figures are 23 and 77. So when you say 21%, you must say percent by volume. Please remember that, because only the good engineers are knowing the difference. Now you know it. Let's have a look to the first line. 1 kilomole carbon goes into a chemical reaction with 1 kilomole oxygen. The result is 1 kilomole CO2. As you see, from 2 kilomoles, only one is resulting. We are multiplying this relation with 12 and dividing by C, small c. 12, why? Because the mass of the carbon is 12 in the Mendeleev table. And C, what is C? C is,
I'm not sure.
this C is the quantity
Carbon.
of carbon in 1 kilogram of fuel. So the first line becomes as you see it. So 1 kilomole is, instead of 1 kilomole, we are writing with 12 kilograms, yes? And the rest remains. Now we are dividing with 12 and multiplying with C. So the result is what you see here. C kilograms of carbon enter a reaction with C per 12 kilomole oxygen, and the result is C per 12 kilomole CO2. This is the needed quantity of oxygen, and this is the needed quantity of CO2 in the flue gas. And this is the used quantity of carbon for each kilogram of fuel. So if you want, we can give an interpretation to this last line. In order to organize a perfect combustion of all the carbon contained in 1 kilogram of fuel, one needs C divided by 12 kilomole oxygen, and the result is C divided by 12 kilomole CO2. Kilomole is a unit for mass as well. It is equal to the molar mass expressed in kilogram. If you understood this interpretation that I gave you, identically you can deal with all the reactions of hydrogen, of sulfur, of so on. And finally, we have to decide how much oxygen do I need in order to have have a perfect combustion for all the elements that are here burning. Coal, carbon is burning, hydrogen is burning, sulfur is burning, nitrogen is burning, but normally the quantity is very small. So in a lot of calculation, it is neglected. But water is not burning, and ash is neither burning. And what you see here is oxygen. This oxygen doesn't burn, but it can help to the oxygen coming from the air to run the combustion. So if we want to know how much oxygen do I need in order to complete burn the coal, the carbon, the hydrogen, and the sulfur, I have to make a sum of this element and this and this, and
For N also?
and minus this oxygen, because this is already available. I must not bring it from the air. Yes? Okay. You must know that in normal air, we have also humidity. Here it is a value given that is specific to Romania, but the humidity in your country can be different. The air is, I don't know, more humid than here, I don't know, or less?
No, it's less.
It's less, okay. So if we want to find out what is the minimum oxygen quantity, I have to add these four terms, this with this with this, yes? Meaning this, and this. And I use a transformation from kilomole into normal cubic meter. And this why the term 22.41 appears. This is the molar volume of each kilomole for every gas under normal condition. So a kilomole of gas in normal conditions has a volume of 22 square meters, cubic meters. Yes? So this is a constant used in thermodynamics. And as you see here, minus O divided by 32, it is this.
Yes.
This. 32 from where? The molar mass of oxygen, 16 plus 16. Yes? And if you make the calculation, you can have the result also in kilogram as you want. This is the unit. But the result is you can calculate this minimum quantity of oxygen either in a cubic meter or in kilogram or in kilomole as you wish. If you analyze the more complicated situation, but logically similar, of the combustion of gaseous fuel, you will have as result what is here written. And I can prove you this, taking into consideration this reaction, this and this, of hydrogen, of CO, and of hydrocarbons. And the result will be, as you see, a sum between the oxygen needed for the combustion of the hydrocarbons and the combustion of CO and H2. Here, don't forget this F. F means from the fuel. All these values are numbers of kilomole, are numbers specific indicating how much oxygen or hydrocarbon or CO or hydrogen are comprised in one unit of mass of gaseous fuel. So in order to use the air, the cheapest way is to take it from the air. And so we are calculating the minimum amount of L. L means Luft from German. L is air quantity. So it is this O min, minimum, divided either by 0.21 or by 0.23, the well-known participation by volume or by mass of oxygen in the air. Very important are always the units. In order to be sure that every molecular of that can go run a combustion meets the necessary oxygen content, means we are using an air excess ratio, meaning in order to be sure that the combustion can take place, we will introduce more air as minimum necessary. And the value for this excess air ratio, lambda, is normally over 1, meaning we are introducing more air than minimum is necessary. You understand? It is like a security coefficient. Yes, because combustion is, how to say, two molecules must meet together. One is oxygen and one is let's say carbon molecule. And in order to be sure that all the carbon is burned, you can say, okay, I introduce more. I introduce, let's say, 2 molecules of oxygen instead of 1. So I have to introduce more air. The disadvantage of this air excess ratio is that with the oxygen that has a positive role, you are introducing also nitrogen. So the values for the air excess ratio cannot be 10 or 11 or 2 or 3, because this would mean a lot of nitrogen carried through all the combustion facility with no use. Supplementary, you need more space. The pipes must be more larger. Everything is much more complicated. Not mentioning the fact that nitrogen from the air in special conditions, but this is not the object of what you have to learn. Perhaps you will come here for a doctoral thesis or master thesis, and then we can learn about how to avoid the formation of pollutants, because the nitrogen from the air, when the temperatures are over 1000 degrees Celsius, is turned into NO, meaning a high pollutant. And this pollutant is not originated in the nitrogen from the fuel. It is originated in air, in the nitrogen from the air. So this air excess ratio must be taken under control. Normally, when you run a combustion, we are speaking also about the burners, and the burners are also low combustion NOx burners, meaning that in these burners some methods are taken in order to avoid the formation of NOx, NO2, or NO. And this is done with a value of the air excess ratio less than 1, because NO is coming from a reaction N2 plus oxygen, NO plus, and some coefficient here. If this molecule oxygen, molecule of nitrogen from the air has no oxygen, because the carbon is stealing the oxygen, this is very good for the combustion, because the combustion is perfect in terms of carbon. You use all the energy of the fuel, but you don't produce NO. You understood? So in special cases, this air excess ratio, for avoiding the formation of NO or NO2, named globally NOx, can be under 1. Did you understood me?
Can you repeat the last?
Should I repeat?
Yes, the last thing.
So normally this air excess ratio is over 1. But it must be limited, because oxygen is not coming alone from the air. It is accompanied by nitrogen. And nitrogen can enter at high temperature, reaction with oxygen, and producing a very harmful pollutant, NO or NO2. This is real. It happens also in the atmosphere. And in order to avoid this possibility, you use stage combustion or low combustion burners, meaning that for a particular time and zone in the combustion chamber, the air excess ratio is less than 1. Under these conditions, the hydrogen doesn't find any oxygen to go into the reaction, and it remains molecular nitrogen.
It will not be in the chemical reaction.
Yes, unfortunately, not all the carbon finds the necessary oxygen, and that's why you have to stage to give more air in another stage of the combustion. But at lower temperature, when the molecular nitrogen is not able anymore to enter the reaction with oxygen. Only the carbon can do it. The CO or the carbon can do it and turn to CO2. Is it clear with this air excess ratio values? So remember, you cannot make them very high, but normally they are about 1 and something, except in the gas turbines. And also for avoiding the formation of the NOx, there are real situations where this air excess ratio is less than 1. So less than 1 in the stage combustion, or I told you the low NOx burners. So what we find in the flue gases? First of all, we will find CO2, we will find H2O as vapors,
Vapor.
SO2, of course, the excess of the nitrogen, and also the oxygen that was not consumed. So the oxygen that was not consumed means lambda minus 1 multiplied by L min and 0.21 in order to use the kilomole unit for oxygen. The molecular nitrogen comes from the air, 79% by volume multiplied by lambda and L min. And also it was present in the fuel. So N divided by 28 is the amount from the fuel. For the CO2 and SO2, it is very simple because we are looking back and you see here C divided by 12, yes, and S divided by 32 kilomole. So these values are found here. You see them? For the vapors, it is, you must make a sum of the humidity from the fuel and the hydrogen that through combustion is turned into water. It's clear?
But why we use 12 for humidity? W?
12? This 12 you mean?
Yes, yes. I guess it should be 16, right?
It is this water, this, yes? It must be 16, not 12.
Yes, I guess that.
Yes. No, H2O, 18, not 12.
Okay. But H,
uh,
oh yes, H2O, yes.
Yes, 18, not 12. I don't know. Let's correct it. So for the gaseous fuels, it is the same, but the formulas are more complicated. more complicated, but the idea and the logic demonstration is the same. All these formula are to be found in thermodynamic tables ready-made. You don't have to learn them by heart. You must know only what each letter represents. Yes? And of course, you must know the value of lambda. So, normally the flue gases are analyzed by analyzers. And here I gave you an example of such of gas analyzer, flue gas analyzer. It is the analyzer that we use here in experiments. And as you see, here are the flue gases. And from the flue gases, a part is sent to special devices. All these 15 up to 19 are sensors. Sensors for oxygen, for CO, for NO, SO2, NO2, and so on. And separately, there exists a pressure and temperature measurement. Separately, all this system is warmed up, because if you don't keep the gases warm, if the normal pressure is the pressure outside is normal, you have to keep the temperature of the flue gases over 100 degrees, because otherwise what happens? The vapors are condensating and form water, liquid water. And this liquid water with the NO and CO and whatever CO, SO2 in the flue gases will form acid, and you will have a acid corrosion in the instrument. This phenomena is occurring naturally outside. Outside, you have heard about acid rain. What is acid rain? Acid rain is the combination of pollutants such as CO, NO, SO2 or NO2 with the condensed vapors from the free atmosphere. And instead of having a rain with normal water, you have it with acidified water. Yes, and this acid rain affects very much the vegetation and the paintings and the buildings and the historical monuments and the sculptures and as you see, yes?
Yes, yes.
And not mentioning the losses in the agriculture, because all the vegetation is affected. The phenomena is known as forests are dying, yes, after such an acid rain. So, do you have a TV, or do you can have now information? Zaharian sand is coming over Romania, so it is not good to next 2 days to go out.
Yes, it looks cloudy.
So have a look to the internet. So very important for the quality of the fuel is a value named heat of reaction or heat of combustion. Normally, it is a standard value. When you buy a fuel for industry, you don't say, I want to buy oil. You say, I want to buy oil having minimum heat combustion of so on and so on. Yes, it is the useful part of the fuel. And this heat combustion comes from what?
Calculation.
From this preliminary chemical analysis, because it depends of how much carbon, hydrogen, sulfur you have, of how much hydrocarbons and hydrogen and CO do you have in the gaseous fuel. So this is the quality of the fuel is first of all indicated by this heat of combustion. That is in close connection to what? To the composition of the fuel. Yes? The heat combustion can be measured experimental in a calorimetric bomb, or it can be calculated. This is how such a calorimetric bomb is constructed. This is for solid and this is for gaseous fuel. The idea is that you have to organize the combustion of a known amount of fuel and measure how you can the resulted heat energy. And then this heat energy divided by the quantity of fuel gives you the heating value. In literature, you will find two heating values, the upper and lower value. One is named also the gross heating value or net heating value, the other one. Please remember that always you can use only the lower heating value. And now I will explain the difference between them. The lower heating value, as the name says, is a value less than the upper heating value. So the flue gases are containing a lot of gases, CO2 and nitrogen, and what else? I ask you.
Oxygen.
Oxygen, yes, and?
Carbon.
No, carbon, no. Humidity, vapors.
Oh yes, humidity.
Yes, vapors. But if these vapors are remaining vapors, it is okay. But if these vapors are condensating, this phenomena is also exothermal. And normally, if you cool down the flue gases, the condensation occurs. And a part of heat is generated, but this heat you cannot use it. It is not the real heat of combustion. It is a heat that you can use only in very special situation by using the condense. Do you understand me? This condense cannot be normally used. If it is used, it is okay. So normally, when you will buy fuel for your company where you will work, you must look at the lower heating value. Let's speak some more about the quality of a fuel. The quality of a fuel is indicating by the heating value, especially by the lower heating value. this is based on the composition of the fuel. And the composition of the fuel has two parts. One part is the elements that can go into a combustion and into an exothermal reaction, produce heat or transform the energy of the fuel into heat energy. And the other part is are elements or parts that are not useful, not at all. As example is the ash. So the ash, if you use fuel, solid fuel, and even liquid fuel, the amount of ash can be larger or less larger, but it is there. And the result are the particles in the flue gas. So in addition to the NOx and SO2 as pollutants and the CO2 as green gas, greenhouse gas, generating the greenhouse gas effect, you have also the particles. So the less ash is contained or zero ash, the better the fuel is.
Mhm.
So normally, let's take an example, the lignite from Romania. It's a solid coal, and it contains also in some situations 70% of ash and water. So carbon is about 20%. So meaning in 1 kilogram, you have 700 water and ash, 200 grams of carbon, and the rest is sulfur and oxygen and nitrogen. So you use only 200 grams from 1 kilogram because the rest, 700 grams, is ash and water that you cannot use in the combustion. But you have to do the combustion because lignite is a fuel that is available in Romania, or I don't know, you in your country perhaps you are using gas, more gas, but I don't know if you have also power plants on solid fuel, I don't know. But I think in the future you will turn to solar and photovoltaic sources. What is the largest disadvantage of this renewable energy sources, on your opinion?
The big law of materials.
No, they are not continuous. You can have the solar energy only when the sun is shining.
Mm.
Photovoltaics as well. So in order to use this energy, the solar energy, in solar panels or photovoltaic panels, you need special technology first of all, and then uh, uh, heat accumulators or energy accumulators, so that by night, when you don't have the light of the sun, to have sufficient energy accumulated to run the power plant. And this is not the situation presently. Nobody knows how to do this very large energy accumulators. You know, in cars you have accumulators, yes?
Not sure what is it exactly.
Hmm?
I'm not sure what is it exactly.
This it is a device where the energy, the electric energy is stored,
Huh.
and you use it uh, not when it is produced, you use it when it is needed.
Mhm.
In a normal vehicle, you have an electric accumulator.
Yeah, yeah, of course. Now I know.
You know what, yes. But for a big power plant, this is not invented up to now. Or if it exists, it is huge, it costs a lot, and to produce it, it costs a lot of CO2. So the global value is the same. It brings no success. Uh, Finally, we are interested how much from the available heat energy, fuel energy, you can use in this combustion facility. And this is expressed by the thermal efficiency of the facility. So in this lecture, you learned about how to organize and understand a combustion process, how to calculate the needed air and the resultant flue gas amount. You learned also about how important is to know the characteristics of the uh, chemical composition of the fuel. You have to, you understood also that the fuel must not be the classical fossil fuel. It can be also a renewable fuel like a bio source, biogas, biomass, agriculture biomass, and so on. And the combustion is the source not only of the heat that you need in order in a power plant, but also the source for pollutants, pollutant generation, and CO2 generation, because CO2 is always organized separately. The quality of the fuel depends on the chemical composition that is, let's say, responsible for the value of the heat of combustion. So we can close this this lecture now. Yes.
But I just want to make sure about the 1 meter square normal.
1 meter. Yes.
Yes.
Okay. I am dictating you one. It is not.
It will be the molar mass
No, it
in
is
the.
not molar mass. It is the mass
Mhm.
of gas.
In the normal situation.
In a normal situation, comprised in a volume of 1 meter.
In 1 meter squared.
Not squared. It is squared means two.
Cubic. I'm sorry. Yes.
Cubic. Yes.
Yes. Yes.
So you can imagine a bottle or a can of 1 cubic meter, and you put inside a gas. Gas number 1, gas number 2 separately, yes? And
And
if the temperature and pressure are normal, meaning 1 atmosphere and 0 degree Celsius,
then I calculate the
mass
mass.
is 1 cubic meter normal. Yes? Okay. Other questions?
No, thank you. Thank you.
Yes. So I we can now go through another through another lecture. Are you available for another lecture now?
Yes, yes, but
Yes.
because
Let's.
these days I'm fasting and I will start cooking at 8 and 10 minutes. So if it's okay to
So
finish at 8 and 10.
this lecture has 16 slides. Yes.
Mm.
Okay. Uh, I will prepare you further another essay and also another how to say um, solved problems in order to give you the possibility to uh, to see how thermodynamics problems can be calculated. You are having already, I think, 4 examples,
Yes,
and you must do them by yourself, calculate by yourself. Be
yes, yes,
attentive. All the files that I uploaded in the campus, and not only me, perhaps the others also gave you some lectures. You must download them and keep them, because I don't know if from abroad you can uh, go into the campus, because in end of September the campus is cleaned up, because
uh-huh.
we start another year. Hmm? Are the other professors also giving you information to study?
Yes, for the other courses, I'm already following, and it's okay.
Okay, so you are okay.
Yes,
Uh, so I don't know, you must in June you must uh, uh, contact this professor, what is his name, Frigura, yes, in order to give you all the documents, signed documents. Don't go away with no signed documents.
yes, yes, of course.
It's very important, because they will say, okay, we will send it by email. No, you must have it now when you go back, because you don't know what will happen.
Okay.
Yes, and you must have your credits, not to lose uh, these months of study, because
Yeah,
they are months from your life.
of course.
Yes. Uh, okay, now we are going to learn about gas power cycles run with perfect gases. You know what the perfect gas is it's a real gas, but that has a low density
Hmm.
and low pressure, high temperature, and it has some particularities that are resembling to the model of the ideal gas. Cycle means a series of transformation that have the initial and final state identically. So it is when you go from A to B, and from B to C, and from C back to A. Yes, this is a cycle. During a gas power cycle, work is generated if this cycle has a clock sense, and it is named engine cycle.
Hmm.
If the uh, sense is trigonometric, it is a case of the refrigerating and heat pump machine, and the cycle is named heat generating cycle.
Hmm.
The scope of the engine cycle, work generating cycle, is to produce work. In order to produce work, according to the second law of thermodynamics, you know that the system must be in connection with two heat reservoirs with high or low temperature. It is not possible to be in connection only with one reservoir, because this will mean that all the energy received by a system is turned into work, and this is not possible in reality. It will be an ideal case, but it is not possible in reality.
Yes.
Always a low heat reservoir must exist, and this is normally the the atmosphere, the environment of a system. The efficiency of an engine is defined by the ratio between the produced work W and uh, the energy of the high heat reservoir. And if you use the uh, relation of continuity, meaning that high Q high plus Q low, this is with plus, this is with minus, that we have to put it into brackets to take only the positive value. The sum is W, because energy is conserved. It is not produced, but it is conserved. So the work comes from the high heat reservoir minus the low heat of the reservoir. And minus means these brackets. For the heat generating cycles, we don't have efficiency, but we have coefficient of performance. So for the heat pump and for the refrigeration machine, we are using the same idea as for the efficiency. We have to make a ratio between what we are useful generating and what is the input for this. For a heat pump, you use the energy that is heated, yes, divided by the work, because the heat pump, you have to put it to electricity. The electricity moves, makes the work, mechanical work, and this is the input. And because it is negative, it is because it is received, it is also put in brackets. Yes? And the refrigeration machine, it is the same idea, but at the refrigeration machine, you use the heat of the low temperature reservoir. Yes, and in between them, this relation is so. Here is a schematic of the engine and of the refrigerator and heat pump machine. Yes, these are here. It is a sense: in, out, out, in, in, out, out. We are having for engines normally a thermal efficiency classically as ratio net work output divided by the heat introduced into the cycle, and this is positive. But we have also a lot of other characteristics that I don't go now into detail, but here they are presented. But the most important is the thermal efficiency, and sometimes it is also the mean effective pressure or the compression ratio. Yes. So, and the basic cycle in thermodynamics, the basic is the Carnot cycle. The Carnot cycle consists of two isothermals and two isentropes. This is a PV diagram, and this is a TS diagram. In a TS diagram, the isothermals are two horizontals, and the isentropes are reversible adiabatic. S equal to constant are the two verticals. So 1, 2 is isothermal compression. 2, 3 is a isothermal isentrope, isentrope compression. 3, 4 is isothermal detention, and 4, 1 is also a detention but isentrope. And here is the same. These 1, 2, and 3, 4 are the isothermals, and 2, 3, and 4, 1 are the isentropes that are reversible adiabatic processes. So you must know it is let's say basic knowledge to know the Carnot cycle. This is the engine Carnot cycle. Yes, it is the cycle with the highest thermal efficiency when it runs between the two extreme limits of temperature.
Opa, está tudo. Tá. Sorry? Está tudo a andar, não sei o que é. Olha, velho, estou a ligar porque precisava da tua ajuda.
Can I continue?
Yes, of course.
So it is a theoretical cycle, and it used only for comparison. It is an ideal cycle because in reality nobody can realize it. And remember, the efficiency has a very nice formula: 1 minus ratio, the minimum and the maximum temperature expressed in Kelvin. So with only two information, the minimum and maximum temperature, you can calculate the efficiency of the potential ideal Carnot cycle, and if this is the maximum that you can achieve with an engine running under the same conditions and limits of temperature without losses. Is it clear for you? This value, this formula.
Tu diz-me para eu falar em thermal spray. Yes, yes, it is. PVD, CV.
I don't know, do you speak with me or?
My roommate was PVD also. But yes, I understand this problem.
Ele tem aqui TVD, CVD.
Hello?
Sabe o que é isso quer dizer?
Hello?
Okay, let's continue because I have no time. You can speak with your roommate later, yes?
No,
Okay,
yes, yes,
okay.
he's
Mas
speaking in the
vai,
phone, but for me, yes, I understood this.
Conteúdos da position é
So
basicamente.
please don't speak, both of you, because I can't hear you clear. Only one must speak. Another very well-known cycle is the Otto cycle. You know, cars are, if they are running gasoline, they are running Otto cycle. It is also what we are analyzing here. It is also, let's say, ideal Otto cycle. It is formed by isentropic compression, 1, 2, isochoric heating, 2, 3, isentropic expansion.
Eu acho que não vou haver mais feliz para fazer para os detalhes.
So please don't speak with with your mate, because it is disturbing me. If you want, we can close the lecture and you can speak with your mate.
No, I'm not speaking with him. He's speaking in the phone. So sorry, I will mute my mic.
And isentropic expansion, 3, 4, isochoric cooling, 4, 1. This is the Otto cycle in PV, and the same is in the TS diagram. According to the compression ratio, epsilon or whatever, the ratio between V1 and V1 and V2, the formula for the efficiency is not as simple as the Carnot formula, but it is not very complicated. Gamma here is a adiabatic exponent of the gas. Yes, and epsilon is a compression ratio that is normally known. Another cycle is a diesel cycle. The difference is that the diesel cycle is running not gasoline, but what? Diesel fuel.
Diesel.
Yes. Okay. And the combustion for the auto took place during this isochoric heating, 2, 3. So it is an isochoric process. At the diesel, the combustion takes place from 2 to 3, that is a isobaric process. So the heat addition is at constant pressure. If you, the main difference between the two types of reversible cycles is the value of the temperatures, because in the Otto cycle, you must need an external source to start the combustion, external flame or ignition system, yes? But for the diesel, the combustion is a self-combustion. It starts to burn from alone without any other intervention, because by compressing, the temperature of the gas is going up and up, and finally the gas starts to burn. So what you want to avoid by the Otto, you need by the diesel cycle. So for the diesel cycle, you must know also these 4 processes. And in addition, another coefficient is indicated, and thus the efficiency is a little bit more complicated. But as I told you, it is not important to know all these formula by heart. Yes? Have a look. The auto engine in the 19th century, in the middle, and the diesel at the end. Yes? And it is, I don't know, I hear all your colleague in the room. I will propose the next lecture for Saturday. When?
15th of May. Right?
At what hour? At what hour the next lecture?
It was 6:30.
So 18:30.
Yes, 18:30.
18:30. Okay, we will finish this this lecture, and then we will finish this Zoom. So the dual combustion cycle has not 4 but 5 processes, and the new aspect is that the combustion is both isochoric and isobaric. So it is done in 2 steps. And the formulas are much more complicated, but I told you, you have only to know how to use them, not to learn them by heart.
Right, yes.
The Joule cycle is the cycle for the gas turbines. The gas turbines are very beloved nowadays because as I introduced you already, the gas turbine cycle has the property to turn the energy of the fuel directly into heat energy, and after that mechanical energy. You do not run the producing of heat energy of flue gases that is turned to the heat energy of vapors, and the vapors are going into the turbine. By the gas turbine, only the gases are used. We don't have any vapors. So the cycle is much more convenient, and it is something very beloved nowadays. So the Joule cycle is composed by 2 compression, 2 expansions, isentropic compression 1, 2, isobaric heat addition, combustion 2, 3, isentropic expansion up to the initial pressure 3, 4, and isobaric cooling to the initial state 4, 1. And the expression of the efficiency of such a cycle is also indicated. It depends very much on the ratio between the 2 pressure levels. For example, in this particular case, an example is that P1 is 1 bar and P2 is 4, meaning phi is exactly 4. And if you take gamma 1.5 or 1.4, you can find the value of the efficiency. So the combustion engine is running a lot of succeeding processes at high and low temperature. You have, but you have to respect that the temperature inside must be far above the melting points of the metals inside. Yes. So you cannot imagine an internal combustion engine running a temperature of 2000 degrees, even you would like it. But because at this temperature, no metal is resisting. So here is an example of this an auto named spark ignition engine is working. It is operating in 4 strokes, A, B, C, D, and you see here the crank, the crank pins, spark, the cylinder, the piston, the connecting rod, the intake and exhaust valve, and so on. They are all very important elements in the construction, in the schematic of a spark ignition engine. So I think you understand well this
Yes.
aspects. So you have to make the difference between the auto and the diesel engine, because you for the auto you must avoid very high temperature, meaning the compression ratio is limited, and the compression ratio for the diesel engine are much more higher, because you have to reach a high temperature for the self-ignition of the fuel. The idea of diesel was to simulate, to create a Carnot cycle, but it is not possible to create it. But he tried, and the result was successful. You must know that at the beginning, Rudolf Diesel did not use the diesel fuel, but he used a biofuel. Very, very interesting. And now, after so many years, we are coming back to his main idea. Based on the explanation I gave you, that biofuels are also generating what? CO2, but this CO2 is neutral. You remember, yes?
Oh, okay.
So here is a sketch about how gas turbine cycle is working. So air into the compressor. The compressed air is going to the combustion chamber, where you have an oil burner or a gas burner. So fuel in, flue gases are resulting. The flue gases are going directly to the gas turbine, and finally they go out. But the gas turbine is put into movement, and the shaft is rotating also the compressor and the electric generator. A much more sophisticated system is that one with the regenerative system. These gases here in the exhaust are very warm, 600, 700 degrees. It is a pity to send them to the environment, not mentioning the damages to the environment. So the idea is to use their heat into a heat exchanger before the gases go out. The gases are cooled down and give their heat to the air compressed air that is already heated, but not as much as after they pass a heat exchanger. So this is the main idea of the regenerative gas turbine system. And another idea is with intercooling. In order to realize a higher degree of compression, you use two compressors, but in order to keep the temperature under control, you must cool down between the two compression periods the temperature of the air. So this is happening in an intercooler, and the water that goes in and then out is warm water then that you can use to as it is as warm water to wash, to heat, and so on. And the rest is the same. So the gas turbine has to have an action for both compressors and the electrical generator. So this was the end of my lecture. I hope you understood everything.
Thank you very much.
So I will schedule you a new Zoom okay, I must make print screens. Auto participants. I must make some print screens. Okay. Okay. So you learned today some special, very important aspects. What are they? You learned about combustion, and what else?
The gas and diesel generators.
The cycles, you learned
power
about
cycle gas,
combustion
yeah.
and the power cycles with perfect gases. And the next lecture will be about gas cycles with real gas. The Rankine, yes?
What is it?
The Rankine cycle.
Okay.
Okay, so I wish you success to finalize the first homework I gave you, and the next will follow. Be attentive. Yes?
Okay.
Okay.
Thank you.
So end of the meeting. Almost 2 hours are. And please use the YouTube registration because sometimes it is of help.
Yes, yes, of course.
So I am stopping the recording.